Hi, welcome to the June 15th meeting of the Kubernetes IoT Edge Working Group. For today's meeting on the agenda, we've got two presentations. The first one is on container device interface in conjunction with the Container Orchestrated Device Working Group. The second presentation is going to be on K0S and its approach to air-gapped edge environments. So with that said, let's move right on. The first talk will be started by Patrick Ohly from Intel. Go ahead. I think you've got co-host permission.
Yeah, thanks. So perhaps as a more background for the reason why we are here, Sasha and Kate and we met at the recent KubeCon, and we figured out that something that we've been working on with container device interface and dynamic resource allocation may also be relevant for the ACRI project. And we've been asked to basically present here to share what we've been doing so that everyone who is interested in working on ACRI can make up their mind and perhaps also can take a look at the current CAP that we have pending about dynamic resource allocation. Well, the work split is basically that Sasha has been driving the underlying container device interface work. That has been progressing, several container runtimes now supported. What it does is essentially giving a container orchestrator like Kubernetes the ability to inject additional devices, environment variables into a container in a fairly generic format. I don't have too many details about that because it's been moving along fine. The contentious part right now of the work that actually that's really needing attention right now is the dynamic resource allocation and scheduling part that I've been working on. That's where we are taking CDI at the lower level and try to think about what a Kubernetes API might look like that actually takes advantage of these new capabilities in the runtimes. And it's clearly related to the current device plugin API and its limitations, because as you know, in ACRI, it does have its limitation. It's supposed to be used for node local resources. You have workarounds for that in ACRI. It doesn't support arbitrary parameters like strings or booleans or anything. It's really just about counting things that can be counted. Then there are questions about the life cycle of a resource allocation that are not handled well because it's tied to a container. It can't survive longer than the container itself. All of that leads us to an approach where we are trying to do something that is closer to how storage handles a volume. So we have a concept of a resource claim that matches the persistent volume claim. We are trying to build something that is where vendors can extend Kubernetes just by writing a plugin. We call it resource driver, where the resource driver handles all of the resource-specific limitations that then Kubernetes doesn't need to know about. Whether it's available on multiple nodes or just a single one, that's all handled by the resource driver. And we also want to support an easy deployment. So reconfiguring the kube scheduler is something that is both hard to do or in some managed clusters not supported at all. So an approach that relies on scheduler extenders to do something similar wouldn't work for several users. So our approach from a design perspective is based on communication through the API server by updating the resource claim status. That's the shared scratch space, basically, where the different components store their state and communicate what the current state of a resource claim is, whether it's allocated, whether it needs to be allocated for a certain pod or for a certain node. All of that is handled by the resource claim status. And because the resource claim is also a separate object, it can be referenced by multiple pods, either at the same time or one after the other. So if you have a complex device that's hard to set up, then it might be beneficial to just have a resource claim created once for that device and then amortize the cost of setting up that device by running multiple pods against it as needed later on. We took some other concepts from volume provisioning. We do have a resource class that is owned by the cluster administrator. That's where some common parameters, privilege parameters are set, and it also identifies, with quotation marks here, the provisioner, which is the resource driver that handles this resource class. And then the resource claim has the parameters that the user is allowed to choose, which may be amount of RAM that it needs from a GPU, or for an FPGA, which kind of program is supposed to be pre-programmed into it. And then the port spec needs to be extended because we really can't use the existing resource fields to handle resource claims. There's nothing where we could reference them. We could use an annotation, but that's not a proper Kubernetes API. So we are proposing to have something new in the pod spec and have this properly supported by core Kubernetes. That's the key difference compared to something done out of tree with annotations. We are really aiming for something that will be supported by a future Kubernetes out of a box, and ideally also will become a requirement for a conformant cluster.
Are you ready to take questions as you present, or would you rather?
I am.
Okay.
Feel free
I'm just kind of curious. I like the model of using what's gone before on the persistent volume claims with the CSI storage interface. And I actually worked on that spec years ago, holding the formational meetings, so I'm quite familiar with it. But I'm wondering if you've gone so far as to pick up the other things related to it, like namespaces, so that these things can have some semblance of governance, and maybe even that there are techniques in there that align certain CSI drivers with the ability to embed secrets, so that if these devices you're talking to need authentication, you might be able to handle it in that process too.
Secrets are not part of your official API, but they don't need to be. In my opinion, these can be additional parameters provided as part of the driver installation in some custom parameters, some custom TRD, or just really the parameters that the deployment of the resource driver itself takes, the content, the pod parameters or program parameters. The user doesn't, well, yeah, I can see some cases where these parameters might be something that the user needs to specify because it's his credentials. That can be handled by the custom parameters that the resource driver supports. We fully support custom parameters with CRDs. That's the latest iteration in the CAP, where the resource driver creates a CRD that describes which parameters it accepts. That needs to be in a separate object because that's how CRDs work. And then the resource claim doesn't actually embed the parameters. It references this external object. And that object then can have user-supplied credentials or secrets to actually get access to a resource. And that's outside of a CAP because we don't make any assumptions about what the parameters mean. They get published and referenced in Kubernetes. We expect resource drivers to be Kubernetes specific, so it's not as generic as CSI is. We don't have plans to support other container orchestrators, simply to keep it, to keep it simple. This is Kubernetes specific. So what a resource driver then does, it basically watches for these parameter objects and can take whatever it needs to know from there. We don't need to pass it through some generic component like we do in CSI with the sidecars. it is a bit simpler in that regard. As you mentioned, you work on resource claims. I also decided to merge resource claim and persistent volume claim and persistent volume into one object. That solves quite a few race conditions that still exist nowadays for volumes, where a volume might leak if one of these objects gets deleted at the wrong time. Protection against that is not complete yet in volume provisioning, unfortunately. Work is underway.
One of the things that historically has been ugly with those volumes is even something like a Kubernetes cluster node crash. It owned some resource and getting it cleaned up. And if we can maybe learn from history and try to.
I tried.
Yeah.
I really tried to keep that whole resource claim self-contained, so that at any time, that's the source of truth, and it really represents what needs to be done next. It implies that there will be more API calls to update that state, which is kind of one of the objections that I'm getting from the reviewers, that this is putting a higher load on the API server, but it also at the same time is more secure, because we can rely on etcd storing an atomic update and not losing that state. And it also protects against concurrent modifications of that same resource claim. We can have multiple components multiple schedulers trying to use the resource claim for a pod, and only one of them may get access to it, because the API server will serialize updates, and only one of them gets applied to the actual database. So yeah, that's what we are currently discussing in the dynamic resource allocation cap. It's under review. I think that's on my status slide. Let me perhaps show how we envision this whole thing to be implemented. So we do have core Kubernetes changes that we need to make as part of the cap implementation. There will be a new controller manager, or a controller in the controller manager, that handles embedded resource claims. That's modeled again after what I did with generic ephemeral inline volumes for volumes. It's the exact same concept. A pod spec describes everything that it needs from a resource, but then the controller creates the actual resource claim object, and the rest of the components almost never sees or needs to do anything with the embedded information. It will still work on the normal separate resource claim, but that's also where we store the updates and the state. Then the scheduler needs a new resource plugin that knows that a pod that references a resource claim can't be scheduled unless the resource has been allocated and reserved for the pod. These are two separate things. We have resource claims that might be persistent, so they are allocated, but they are not really assigned to the pod that currently wants access to it, and it might not be able to get exclusive access because some other pod is also trying to get that. So the scheduler needs to know about all of that. We do support delayed allocation. That's the same as wait for first consumer for volumes. And in that case, the scheduler is basically taking on the coordination between different resources that might be needed for a pod, different volumes that it also needs. And it basically goes through the usual, where can I run the pod checks? And at the end, it decides that there might be some suitable nodes, and it will try to allocate the resource claim for those nodes. But this might not go wrong, might not go well because it had outdated information. So there is a feedback loop described in more detail in the cap, where it's trying again elsewhere until eventually everything is ready for the pod, and only then the pod gets scheduled. I think in the cap I was discussing with Kate whether Arcri handles that scenario, and we may come back to that later, because I think there are some challenges with doing the same thing with a device plugin interface, because kubescheduler has an incomplete view of what the extended resources really mean if they are shared between nodes. But let's not discuss that now. It's let me just finish here, and let's describe the resource driver. That's the out-of-tree component. So kubelet, when it sees a pod, it it needs to know how to inject and where to get the CDI description, the CDI files. CDI is based on JSON files that describe operations that the container runtime needs to do. And those files get created by the resource driver on the node when a pod is scheduled to the node. And the kubelet needs to call a prepare call once on the node before it can actually start containers. And that's what happens locally on the node between the resource manager, or I think it's now called the CDI manager in the latest prototype, and the resource kubelet plugin. The resource kubelet plugin, that's part of the resource driver that runs on each node where resources may have to be made available. The resource driver controller, that runs as part of a control plane, either inside the Kubernetes cluster or potentially outside of it as a standalone process. That's the part that talks with the scheduler through the API server to mark a resource claim as allocated. And internally, the resource driver controller and resource kubelet plugin, they still need to communicate somehow with each other or track which resources are available where, but that's an implementation detail of a resource driver. So the CAP doesn't prescribe a certain way of doing it. There is one section that where I outline my ideas how it could be done with CRDs, and it sounded like Acquia already is doing something like that. So your path towards using dynamic resource allocation might actually be fairly easy, but of course that would need to be validated whether it makes sense. This whole CAP needs to be accepted first and so on. But at least it seems conceptually similar. So that leads me to current status. We had tried to get this CAP accepted for 124, but there were too many open questions. And as always, those questions just came up when people actually started reviewing CAPs were shortly before the deadline. So we never fully clarified all of them. Right now, Tim Hawkin is our main API reviewer. He had some questions about the API design, so we need to finalize that. Scheduler performance is a major concern because obviously this whole CAP is more flexible. It tended to be more flexible, but with flexibility come additional costs, like calling out to the resource drivers one way or another to do checking of where resources are available. And that's harder to do and slower. It's expected to be slower than the current extended resource model for simple resources. But that's simply the price that we have to pay for this extra complexity. And I just don't see a way how to make the current model flexible and fast. So something has to give here. The question keeps coming up whether that is the right compromise for our users. We just don't know yet. It's part of the challenge that we have. We are just designing this. We have a prototype, but we don't have users. We don't have real resource drivers. So any questions about is that good enough basically has to wait until we have this as alpha and potentially with some multiple resource drivers and real workloads testing this implementation before we can decide that. So I'm kind of trying to deflect these questions, but it's one of the things that comes up. And the last point is cluster autoscaler integration. SIG scheduling asks for that, and SIG autoscaling people are also looking at the CAP. The underlying problem is that we are proposing something that will work within tree kube scheduler, but then will not work automatically for cluster autoscaler, which is an out-of-tree project built on the same source as the scheduler, but then does a few things differently. And SIG scheduling is wary of adding and allowing features in core Kubernetes that are not, then can't be supported by the autoscaler. I'm, again, questioning the attitude a little bit, but it's hard to argue with your reviewers, and perhaps I really need to find a compromise here. The problem is that an out-of-tree component is basically blocking in-tree enhancements, whether those additional out-of-tree features are relevant for users or not. And talking with Kate, I heard that Acquia, for example, or Acquia users are not using autoscaling. So a fictional Acquia that is based on dynamic resource allocation will work just fine without cluster autoscaler support. but we still need to come up with some solution. So the current idea is for alpha in 125, we just outline a plan, and that is in the cap, but then later validate whether that plan actually works, because it will need more further work on prototyping, and hopefully that will convince reviewers to accept the cap, but I just don't know yet. And because we didn't get this cap accepted for 124, we used the time to implement a prototype. If you go to this last pull request, it's basically a pull request from my own repo into my own repo that it has all the commits that extend Kubernetes with a new API, with core components that I mentioned, and work is underway to also support the kubelet changes, but it doesn't have the latest API changes from the cap revisions that we are currently doing for 125, but it's good enough, and it has instructions for building from that branch, bringing up a cluster with a local cluster up, and have this whole thing working. And there's also an example driver in that prototype. And with that, I think I almost made it with enough questions for 5 more minutes for questions.
I just had a quick one question about kind of going back to the pod spec side of things. And you mentioned how maybe you'll extend things by having more parameterization via CRDs. How much can someone specify in a pod spec when they're requesting a device that has a driver behind it? And how is that going to be generalized in the pod spec format?
So in the pod spec, we have at the pod spec level a list that we call resource claims. And the resource claims, in the simplest way, the simplest entry is just the name of a resource claim object. That's for the persistent case. And the resource claim then has the link to the parameters, another object, and that object can be as complex as the resource driver needs it to be. So the entry API.
Sorry.
So the entry API is as flexible as it possibly can be. There are no limitations what parameters are allowed or not allowed.
So a user needs to first look at a resource claim to see, hey, this device is that camera with this frame rate, and then goes and creates their pod spec requesting that specific resource claim because it knows it wants that device with those properties.
Yeah, well, the user creates the resource claim. So they basically write down everything they need in different objects. First the parameters, then the resource claim, then the pod spec or some higher level controller that references the resource claim. So it would be 3 objects that go with an app deployment. The other slightly simpler case is with ephemeral resources, the ones that are meant to be used only by the pod. Then this pod spec resource claims list contains a resource claim template. That basically embeds almost the same information as a separate resource claim object, except that it doesn't get created by the user himself. It gets created by this resource claim controller.
And so every single device will have its own resource claim, or can you have a generic resource claim for a set of devices?
You can have a resource claim for a set of devices if that's how the resource driver works. But the resource claim, each resource claim needs to be handled by one resource driver. But if your resource driver knows how to deal with multiple devices, that's perfectly fine.
And if your device is kind of shared type, so when the same claim can be used in multiple pods.
Okay, that makes sense. But you have to have a one-to-one relationship between resource claim and resource driver. So I guess I'm asking these questions from the perspective of Ohly. It would make sense to run that as one driver and be able to create all these different types of resource claims for different types of devices, or not resource claims, but be able to create, I guess, the potential for users to create resource claims for various different types of devices. rather than having multiple drivers making separate connections with kubelet, which is the case with the device plugin interface, is that you have to create that connection for each individual device, which is fine, but also one limitation that could have been bettered is making it so that you could have one driver make a connection for multiple devices.
Yeah, I think you can make the parameters as complex as you need, and that's where it's basically up to the resource driver to decide what works best for the users, and basically propose your own structure of what goes into the resource claim parameters.
So you mentioned this term ephemeral devices. Could you expand on what an ephemeral device would be versus one that isn't?
It's not the device. The device, of course, exists permanently, but it's the allocation that is tied to the life cycle of a pod. That's what I call ephemeral. That basically means that a pod starts, a resource gets allocated for the pod, and when the pod gets deleted, the resource claim also gets deleted and deallocated. And that creation and deletion is handled by Kubernetes compared to the other case where the resource claim is, or the life cycle of a resource claim is managed by the user. That's the key difference. Everything else, how these resource claims get allocated, is the same.
So to compare, to draw the analogy lines, right now, device plugin interface is always ephemeral devices. So like as soon as the device is requested, where allocate comes to the device plugin, and when the port is done, when kubelet decides what this device is not any longer in use. And if we get this deallocate call to device plugin APIs, then, well, it will be deallocate call. So in lining in the pod spec, like the claim template, we'll be getting similar life cycle what you have with device plugins. But if you have more complex devices, especially like long-lived, like even pipeline of the devices, like in our example is we have a complex FPGA cards which have like multiple components inside. So like the radio encoder, decoder, FPGA, and then special crypto block and network card. So like all this pipeline is something what you set up at once, and when you can use it for a long period of time. So for that, it's better to have different life cycles. So you do allocation, make sure what it's done, and only afterward you start the pods which will be consuming this pipeline of devices.
Okay, thanks. I think I understand. I think we're going to have to call that the last question here so that we allow time for Jussi. So Jussi, can you introduce yourself and your topic?
Absolutely. Let me try to find the correct buttons. I don't usually use Zoom, so.
I think at the bottom, at least in my client, share screen.
Yep, I think I found it.
Okay, and we can see that. That looks good.
Oh, that's wrong button. All right. So I'm Jussi. I'm from Mirantis. And I guess this whole topic started by I think you, Kate, met Edward from our side on KubeCon, and then the topic of K0s popped up, and well, here I am talking about a quick intro to K0s, and I'm of course I believe that we're all quite versed in the basics of what Kubernetes is, so I'm definitely gonna try to focus on the kind of what makes K0s unique and how those sort of things, the kind of how to say it, those differentiating features, how they fit into this Edge and IoT space in general, at least how we see it. So one of the things in kind of unique in K0s is that, well, I don't know unique, but not so obvious at least, is the fact that it's actually packaged as a single binary. So we do it quite differently as K3s does it, for example. So where K3s actually compiles everything in, like you actually have a single binary that runs the K3s process, the kube API server, containerd, and kubelet and everything. So we actually package the K0s binary more like a kind of like a self-extracting binary. So we actually embed other binaries into the single Golang binary by just, it was actually as easy as just concatenating the files into the end of the file. So, and then of course we have to calculate the offsets and everything, but essentially it's like a self-extracting binary. What it actually means is that we can work with upstream components super fast. So say that there's a containerd CVE published. We just basically in our build pipeline bump up the version number, and that's about it. We don't have to worry about like the typical Golang modules dependency. Excuse my French, but hell. I think we've all seen and felt that. So small version bumps in Golang modules are not as easy as they should be. So by doing this kind of real embedding of different binaries gets us a lot quicker doing the different component updates and whatnot. And what it also means is that we're not depending on like operating system packages at all. So if you want to run Kubernetes via K0s, you just install the K0s binary and that contains everything you need. You don't have to worry and figure out that, okay, from which repo I'll pull my containerd packages and from which repo I'll pull my Kubernetes packages and so on. So
can I ask you what the size of this binary is? I mean, the concern I have that maybe you find is just what kind of network bandwidth it would take to get this to an edge location.
Yeah, so it's I think it's like 180 megs currently. So it is a bit hefty, and we know that it's a bit hefty, but then again, by building a big binary reduces a lot of other headaches. So I mean, as in engineering, it's always about trade-offs. So yeah. Yeah, so we don't really have to worry about the operating system packages, and therefore we can kind of more decouple the operating system and then the Kubernetes components life cycles from each other. So you can freely upgrade your OS and everything still works, and you don't have to figure out, kind of worry that if I update my OS packages, will containerd magically upgrade or some other component magically upgrades and everything breaks down and whatnot. We of course include all the needed bits and pieces to run kind of full-blown cluster, but of course you as a user, you're free to swap out some components if you want. So we bundle containerd as the runtime. There's options to run kuberouter or Calico as the networking. And of course we bundle etcd as the main storage for the API server, but we also bundle this Kine and SQLite for the data store for the control plane. If you run like single node masters or controllers, you might want to save some resources and run it with Kine and SQLite only. We all know that etcd is quite almost as hungry as for resources as the API server. So, but as I said, you can run with basically any CRO runtime. If you want to install Docker, just install Docker and run it. But we just don't embed all of them, of course. That would be a humongous binary if we embed all the options. So one of the kind of unique things in K0s is a feature that we call like control plane isolation. So and it's actually quite a bit more than the usual isolation by using taints and tolerations. So you can actually place your controller and worker nodes really separate from the network point of view. Let's see if I have some time. I might be able to demo this quickly, but basically you can have different network segmentation between the controller nodes and worker nodes, and or different set of firewalls and NATs and whatnot in between. So what it actually means is that by default in K0s, the controller nodes, they don't run in workloads. So when you spin up a K0s controller process, it'll create the API server, etcd, and all the typical control plane components, but it's actually running those as what I usually call naked processes. So there's no containerd running, there's no kubelet running, even static manifests or anything on the controller nodes. So they are just like your plain Linux processes. What it actually also means is that there's no like CNI stretching between the control plane and the worker plane, because we're not running kubelet or anything on the controllers, so we don't have to stretch the CNI network. Some of the questions I usually get like okay, why is the usual master, or did it actually change to in 124 already to be the control plane role label? Yeah, I think so too. Yeah. So anyway, the why not just use the usual labels and taints and whatnot to mark the control plane nodes? What we faced in the past with different other distros and solutions that we've been building is one of the problems is that RBAC doesn't actually cover the question that okay, is Jussi actually allowed to deploy stuff on controller nodes? I mean, there's no RBAC to filter stuff like node selectors or tolerations or whatnot. And that's actually a pretty big hole, in my opinion, in the RBAC system. And also the fact that the CNI needs to work from node to node and etc. So it kind of assumes that the network is flat-ish, at least. Of course, you can do a lot of fancy things with BGPs and whatnot, but then again, you really have to do that work always for the network configuration. And the API and kubelet connection is something that has always kind of bugged me a bit, that the API requires always direct connection to the kubelets. So when you do this usual kubectl get logs and whatnot, the API is actually calling the kubelet directly, usually. And all this basically boils down to quite limited deployment architectures. So how we do this in K0s and of course we're kind of building on top of giants and big shoulders. So we're utilizing a lot of upstream stuff. So in K0 controller node, there's a component called connectivity server, and connectivity is actually means this API server network proxy SIG groups job or the assets that they are building. So basically the server opens a socket, and then on the worker node we have an agent that connects to that socket. So this basically creates a TLS secured gRPC tunnel which is used as kind of like if you ever used reverse SSH tunnels, this is basically from the concept point of view, pretty much the same thing. So now when my Kube API wants to call the kubelet, say on a node A, it'll actually connect to this server via local Unix socket. And then this connectivity server actually then pipes the connection through this reverse tunnel to the agent, and then the agent forwards the connection into the kubelet to get the logs or execute yourself into a pod or whatever you want to do. So this really allows kind of this kind of like a not disconnection, but kind of like a network level segregation between the worker nodes and the controllers.
Just a quick question here. So in this setup, say you do lose the connection between the controller and the worker node. Does the connectivity server have like cached information there that can be immediately retrieved, or what's the workflow there if it can't get to the agent?
No, it doesn't cache anything. So it's so if the tunnel is broke, then it's broke. So it doesn't cache anything or do anything fancy in that regard.
And so in that case, is that an error case, or is that the specific scenario it's trying to help with by just telling API server try again later?
I think it just returns actually a connection error.
Okay.
So I at least I don't remember ever seeing any like retry laters or anything. So basically how it would manifest itself is like if you do like kubectl get logs or something, you'll just see connection error in your kubectl level. So one of the kind of examples that we've seen in our user base is a case where the control plane is kind of centralized to a regional site or kind of on-premise cloud, whether that's on Amazon Outposts or OpenStack or whatever. It doesn't really matter. I think in this specific use case, it was actually Outposts, if I remember correctly. But anyway, the worker plane is then split into different sites, and a site in this case is actually kind of either like a factory or a part of a factory. So it could be the paint shop part of the factory, or the assembly side of the assembly part of the factory, or the testing side part of the factory. And the workers were actually super small industrial logic controllers that are running one tiny ARM v7 CPU and like a half a gig of RAM available for the whole set of OS and Kubernetes components and everything. The use case is basically that they want to have a super fine-grained controls on how they deploy applications and the workloads that are actually collecting data from different kind of robotic systems and the machinery that's actually doing the assembly jobs and whatnot. So that's why the kind of worker node is this industrial logic controller, which then through the IO bus connects to these robotic systems and whatnot. This has been an interesting, let's say interesting, in a big quotation marks exercise for us. So, and this has been actually a use case that's kind of driven us for some of the choices that we've made. For example, at one point we actually changed the default CNI to be kuberouter instead of Calico, based on this specific use case, because kuberouter is much more lightweight than Calico, and back then, that was like a year and a half ago, back then Calico didn't even support ARM 32 bits. So we didn't really have a choice. Let me see if I can actually pull out quickly one of these. I have some of these boards, so there are these super kind of Raspberry Pi sized, a bit bigger than Raspberries, but these kind of industrial grade controllers that are actually running Kubernetes. I don't have them plugged on right now, so yeah, that's been pretty cool.
Hi, Jussi. This is Sean. May I please ask a question regarding this scenario?
Of course.
Yeah. So I'll be honest. I am part of a company that actually makes its own hardware and industrial grade controllers and everything. So one question is, are the K0S workers over here that you show in the figure, are they actually scheduled from the controller themselves, or are they actually, let's say, hard coded onto each controller per se, like the way you mentioned it over here? So my question is, because most of the times for industrial IO buses, you require, let's say, file descriptors from the operating systems themselves, right? And so how does the controller know which file descriptor is, or where it needs to deploy this particular worker pod? If you know what I mean, right? Like, for example, assembly site has a CAN bus controller, right? And the CAN bus is then available from your operating system on, let's say, /dev/can0, whatever. So how does the controller itself figure out if assembly site worker node actually has that file descriptor, or some form of UDEV discovery protocol or something like that?
The scheduler doesn't really know it. So it's the human that has to make the connection currently, at least. But that's actually where I see a lot of potential in the container device interface that was just presented. So to make the scheduler more aware of these sort of things, because it'll help immensely these sort of use cases.
Yeah. Okay.
Of course, in this case, at least as far as I've been following, of course, I'm not an expert on these industrial devices and IO buses or anything. So, but as far as I know, in this case, the scheduling logic regarding the devices and their capabilities is kind of like a human action. So they know that okay, this node is actually connected to that robotic system, so we can deploy these sort of data collection applications on that node.
Yeah, I think that pretty much answers my question, because let me be honest and blunt about it. It's since coming from the industrial edge side, it is quite conservative when it comes to understanding what actually happens on the floor itself, right? Like, so for example, chances are you buy a controller, you first have to sit down, program it accordingly to your needs, and then you, let's say, figure out a way to extract that data and probably send it somewhere upstream. Doesn't have to be an on-premise cloud or something like that.
Yeah.
But it's yeah, like I said, trickling down Kubernetes on the industrial edge is a bit more tricky compared to standard networking or standard applications, web apps.
Absolutely. But that's also where a lot of the potential and benefits is. So I mean, if you think that how things are done nowadays, so there's actually human going around the factory with a USB stick and installing the different applications in the different controllers and whatnot. So having a centralized way to manage all this via Kubernetes API is going to be fantastic, at least on some day in future. Probably not today yet, but
yeah, I will say you might be able to enable this right now with Ohly. And then you can look and see if kind of the dynamic resource management KEP does that even farther and more specific to your case. But I'm happy to talk about that offline afterwards if you want to talk through the scenario.
Absolutely. I need to get myself first a bit more acquainted with Ohly. But absolutely, yeah. I mean, the minimum system requirements is basically quite modest in a way that we don't embed a lot of stuff on top of the plain upstream Kubernetes. So when you set up K0's cluster, you don't get much bells and whistles. So you get upstream conformant Kubernetes, and that's about it. So we don't bundle and force people to use like Istios and other large bits and pieces. So and as said, especially the worker nodes, we've actually managed to run the worker nodes in these tiny 0.5 gig of RAM boxes with one ARM v7 CPU, and I think that was a nice kind of a surprise that it actually still leaves a bit room for the workloads to run. Air gap setups are supported out of the box, and I mean we don't do any like big magic on air gap setups, but I think the way we've built K0s and how we package it is actually quite simple. So I mean, if you have this typical air gap kind of your cluster runs in a bunker case, then you don't have to worry about installing different OS packages and whatnot. So you just basically have a USB stick where you have the K0's binary and a tarball for all the system images, and that's about it. So basically you need 2 files to set up your cluster. What K0 does for the image tarball is actually on a when it boots up, it finds the tarball in a specific location, kind of predefined folder in a disk, and then it automatically imports the images for containerd. And you can of course have multiple tarball files for your own application images or whatever you need to run on the nodes. What we have found out is that the kubelet image garbage collector can cause some gray hair, unfortunately, or if I'd have hair, it would be gray already. But the main problem is that there's no like configuration that, okay, whenever you run the garbage collection on images, don't touch these ones because these are system images, so don't go and remove them. So we've seen I've actually managed to see a case where kubelet removes the pause image itself. I was like, what? That's weird. And containerd actually even allows you to run to remove a pause image, even though you have like 10 of those pause containers running. I was like, okay, now I've seen probably almost everything, but yeah, I'm planning to try to find some time to see if I can revive the KEP 1717, which is about to define some sort of a configuration for the garbage collection that okay, don't please touch these images. But I haven't yet, unfortunately, found the time, but hopefully in future I'll find the time. All right, that's about it.
Thank you for presenting all this.
No worries. No worries. Glad to.
Maybe I could answer my own question on the project site, but I'm just curious about how much the traction is in the number of users who are deploying this now and the number of contributors you've got on the project.
So number of users is what we've seen from the anonymous telemetry is around like 1,000+ clusters online. So pretty decent number of clusters online, I think. I can't remember the amount of contributors that we have, but we definitely want to see more. Let's put it that way. So it's mostly done by the core handful of people here at Mirantis, and we have seen some external contribution, but of course, as basically as any project, we definitely want to see more contributions.
I know you had a demo that you wanted to share, and it seems like we might not have time for that, but if you do record one and want to share it out, we can still put it in the agenda notes for folks to look at later, or you could even drop it in the working group Slack.
Yeah, or if there's any already out there up on YouTube or something, that I'd like to see it myself.
Yeah, I'll see. I might actually have a recording available already somewhere. At least I remember recording something a while ago, but it's easy to re-record, so I'll put it out in coming days.
Okay, thanks. Say, we've got maybe 2 minutes left. Kate, do you want to give an update on the movement of this group from the Kubernetes project over into the CNCF before we close?
Sure. So it's something that we've been talking about for a month or so, and at KubeCon EU, we presented that we are moving from the Kubernetes space to the CNCF space as a part of this working group. Part of this is because some of the projects we talk about here aren't specific to Kubernetes, and also a lot of Kubernetes working groups are focused on expanding the Kubernetes API, like some of the work that the CDI working group and COD working group actually is working on. And so we're expanding to a bigger scope. And the update of that is that we have merged in our transition to fall under the runtime tag in the CNCF. So as of now, we have all the same links, meeting times, Slack, et cetera, but we're going to start gradually transitioning that over to CNCF. So having a different Zoom link, having a different agenda hosted by the CNCF. I think we're going to move our Slack, but that one's a little hard because I think we do have a good Slack history. So maybe there is something we can do around that of staying in Kubernetes.
Okay, thanks, Kate. And we're out of time. So thanks everybody for attending. We'll get the recording of this up soon. If the speakers can drop a link to your deck, that would be nice. Either patch the link to the deck right in the agenda notes doc, or if you have trouble accessing that, drop it in the Slack channel, and then I'll update the agenda notes doc later. Thanks. So bye everybody, and we'll see you at the next meeting.
Bye,
Everyone.
Bye.